let's first graph that, which will illuminate the thing a little bit.
Okay. Would it be a hyperbola?
Yep. With its vertical asymptote shifted which way?
1 to the right.
Okay. So there's my vertical asymptote. Horizontal asymptote is where?
1.
No, 0. Y equals 0.
0, yeah.
In other words, it isn't affected by that x minus 1, by that transformation. And then it's going to look like this and this. In other words, once you get your asymptote grid on there, pretty easy to draw the curve usually. Okay? And they're saying, where do we have a slope of minus 1? Well, it looks like we got some point right there that would have a slope of the tangent line. That looks like it would be somewhere on that curve up there. There's a slope of minus 1. And somewhere down here there's a slope of minus 1. And only 2 points. Okay? So we have to figure out what points those are. So what do I need to do?
Point slope.
What does slope mean in terms of calculus? The first derivative.
Would it be rise?
It's the first derivative. That's what first derivative means, is slope. So if I want to know the location of this point on the x-axis and this point on the x-axis, then I'm going to take the derivative of this and set it equal to minus 1. What's the derivative of this? Y prime. Let's start there.
Okay, so would it be y equals 1 over x plus 1?
No, let's rewrite y so that it's x minus 1 to the negative 1 power. And now apply the power rule. In other words, there's no need to use the quotient rule even. A lot of times you can avoid the quotient rule. Have you had the quotient rule? You have, haven't you?
Yes, I have.
Okay. But a lot of times you can avoid it by just turning it into a negative exponent. And now I can just use the power rule. Well, start with the exponent, minus 1. The inside is still that. Subtract 1 from the exponent, and then multiply the whole thing by the derivative of the inside, which is 1. So y prime is equal to minus 1 divided by x minus 1 squared. First of all, make sure you know how I got that.
Okay.
In other words, I applied the power rule, and then I just put it in as a positive exponent. In other words, this is the same as what I've circled. Okay?
Yes.
Now, I want to know where the slope is minus 1. Well, that means y prime is minus 1. So now I have an equation to solve. This one right here. And whatever I get for x is going to be this value and this value.
Okay.
Okay, so let's solve that. How do you solve that?
Would I do plus 1?
Well, I can divide both sides by minus 1 to get rid of these negative signs, first of all.
Okay.
Always easier working with plus signs than minus signs. Now the next step, I'm going to multiply both sides by what?
X minus 1 squared.
So I've got x minus 1 squared on the right side, and I got plus 1 on the right, on the left side, and I got plus 1 on the right side. Now, solve that. It's the next step.
Should I factor it?
No? Usually when you have something squared, you want to take the square root of both sides.
Okay, so it's square root.
If I take the square root of the left side and the right side, the left side just becomes x minus 1. Right side becomes plus,
square root of 1.
No, plus or minus.
Oh, yeah, plus or minus 1.
The one thing I try to tell every student that I have is that when you're solving an equation by taking the square root of both sides, always begin your answer with the words plus or minus. Because minus 1 works just as well as plus 1. Minus 1 squared is 1. So that's why it's plus or minus. Okay? Now solve this.
So I'd add 1. So then it'll be x equals either 2 or 0.
Correct. And that's where those 2 points are. In other words, this point here is 2, and this point here is at 0. And on that graph, that's where you would find the slope of the tangent line would be minus 1. Look at the graph and tell me where the slope of the tangent line is plus 1.
Where is plus 1?
Yeah. In other words, let me erase all this stuff that we don't need. Is there any place on that graph where the slope, where the slope is plus 1? No.
No.
Oh, slope's negative no matter where you're at. Negative there, negative there, negative there, negative there, negative all the way down. On the upper side, negative, 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 negative. So if I had done exactly the same thing and set y prime equal to positive 1 instead of negative 1, I would have found no solution. There would have been no point. In other words, I would not have found an algebraic solution at all. Because I would have been trying to take the square root of a negative number, which you obviously can't do. So most important thing about differential calculus is to understand that the first derivative is a slope. That's exactly what it means. In other words, first derivatives mean instantaneous rate of change of the function at some point. Well, instantaneous rate of change means the same as slope of the tangent line. That's why all calculus, differential calculus, starts out with slope of the tangent line. That means instantaneous rate of change. How about 28? Is that on your?
Yes, it is.
Okay. Find the equation of the straight line having slope 1/4 that is tangent to the curve y equals square root of x. So what am I going to do here?
Should I square it?
No, we're not solving anything. We're talking about slopes. Always know that when you're talking about slopes, you got to take the derivative. Put them together. And in fact, I would say for the next 2 months, the first step on almost every single problem you get is going to be to take the derivative of the thing.
All right.
What's the derivative of this function?
Negative square root of x.
Not quite. Let's rewrite the function, first of all, properly, without radical signs, but with fractional exponents.
Okay.
I use the power rule. Take the derivative of x to the 1/2.
So don't I put the number in front and drop the power?
You got it. It's as simple as that. Always start with the exponent.
Okay.
Drop it by 1. What do you get?
1/3.
1/2 minus 1 is minus 1/2.
Minus 1/2. Okay.
Yeah, here 1/2 minus 1. That's what we're doing, right? We're dropping the exponent by 1.
Yeah, that makes sense.
That's 1/2 minus 2/2, which is minus 1/2.
Okay, got it. Because it would bring it to 0 if it was only half, and then the other half brings it to negative
Well,
1/2.
you're subtracting 1 from the exponent. That's all you have to know. If that was x to the 1/3 and I subtracted a half or 1, it would be x to the minus 2/3. So whatever that fraction is, you're going to subtract 1 from it. Okay? Now, so this is our slope at any point. Well, they're saying, where is the slope equal to 1/4? So in place of y prime, I'm going to put 1/4. Now, let me go back. In order to solve this equation, it's easier if it's in radical signs. Well, the x is in the denominator because it's negative 1/2, so it's like that. In other words, what I have circled, both circles are the same thing. Make sure you understand that.
Okay.
Okay. Now, what's my next step for solving for x?
Multiply both sides.
Yeah, cross multiply basically.
Okay.
So if I cross multiply, I get 2 square root of x on the left. I get
Equals 4
on the right. Now I still don't want to square both sides yet. I want to get that square root of x isolated.
That's it.
So square root of x equals 2. Now I square both sides. So I get x equals 4. So right there is where the slope equals 1/4. And if you look at the square root function, kind of looks like that, right?
Mm-hmm.
So they're saying out here at 4, the slope of the tangent line is 1/4. And sure enough, that looks like about 1/4. It's less than 1. Not, 2 or 3. So all these problems you kind of want to get by drawing a picture of it. It tells you whether it kind of makes sense or not, your answer. In other words, if we wanted to know what the slope is at 1, well, that slope's going to be pretty steep. That's probably greater than 1.
So it'd be 1 equals the equation.
Well, no. This equation, they gave us the slope. So they told us what the first derivative was. As opposed to figuring out the slope, I would take this, which is the slope, and evaluate it at x equal 1. Well, that gives you 1/2. So the slope of the tangent line here is 1/2. In other words, you can always evaluate the slope of the tangent line if you have what y prime is in terms of x. In other words, if you have y prime as a function of x, then you can plug in whatever value for x you want, and that will give you the slope of the tangent line on the curve at that point.
Okay.
Okay. 28?
Yes.
H of x is going to represent the height of this thing. And it's going to be 100 minus 4.9 t squared in meters. Notice right off the bat, at time equals 0, the height is what?
Say one more time.
if this is the height, if h of x represents the height,
Okay.
how high is it at time equals 0?
I'm slightly
In other words, what is h of
confused
0?
because I know the height's 100.
That's what it is, because when you plug in 0 for t, this whole second term disappears. So that tells us that everything makes sense.
So it'd just be 100.
They told us that they dropped it from a 100-meter high tower, so the height better be 100 at time equals 0. Okay?
Okay.
Now,
Got it.
I could figure out what the height is at 2 seconds by just plugging in, figuring out h of 2. But they don't want the height. They want to know how fast it's falling. What is its speed? Well, speed is, or velocity is the first derivative of position. So what they really want is h prime of x. That's our velocity function. Take the first derivative, what do you get?
So the first derivative. Would I do the power property?
What's the first derivative of 100, first of all?
Negative 100?
No, 0. The first derivative of all constants is 0. In other words,
Why is that?
the first derivative of this by taking the first derivative of that and taking the first derivative of that. Well, the first derivative of 100 is 0. So that goes away.
Okay, so that leaves a negative 4.92.
No, now you got to apply the power rule on that. Take the first derivative of that. What do you get?
That would be 2 times 4.9t.
There's still a negative sign in front. So that becomes that. There's the velocity function. The reason there's a negative sign is because when something is falling, it's always got a negative velocity if it's going down. If it's going up, it's got a positive velocity. If it's going to the right, it's got a positive velocity. If it's going to the left, it's got a negative velocity. So what is h prime of 2? And that will tell us the velocity at 2 seconds.
Okay, so I would put in 2.
Substitute 2 for t and you get 19.6 meters per second. That's how fast it's moving at the end of 2 seconds. And this begins to show you the value of differential calculus. That could be an extremely valuable thing to know, how fast it's falling at the end of a certain period of time. We could also figure out when it hits the ground, because when it hits the ground is when the height is 0. So it's all I got to do is substitute 0 for that, solve the equation, and that gives me the time that it hits the ground.
Okay.
Next page.
Yes.
I think I can do it by this method. I'm not, no, it doesn't seem to like that method. Maybe if I hit that arrow over there. Now I gotta close it out and open it up again. Whoops. Got the wrong one. I got your no-name.txt file. All right. And we're just going a half hour, right?
Say it one more time.
We're just going a half hour, so we got about 8 minutes. Which one's?
Yep. Sorry, you're just lagging.
What's that?
I said sorry, your voice lagged for a second.
Okay. Which one next? Or which ones do you want to look at in the last 8 minutes?
30, I guess, through like 30 and beyond, as many as we can.
Okay. So here, the height of the rocket, h of x, well actually it's not h of x, it's h of t. In the last problem it was actually h of t also, I just wrote it wrong. That's its height as a function of time. And they're telling us that that is 3t squared feet. Okay? So again, when time is 0, the rocket is still on the ground. How fast is it climbing 10 seconds after liftoff? Well, how fast means velocity. So how do you get the velocity function from the position function? This is a position function right here. When I say height, it's position on a vertical line.
So the derivative?
So take the derivative, always, as the first step. What's it equal to?
6t feet.
And now figure out what the derivative evaluated at 10 seconds is.
300 feet.
Hold on. If h prime of t is 6t, what is h prime of 10?
Oh, 60.
All right. 60, and since it's a velocity, it's got to be feet per second, and it is positive, as it should be, because the rocket's going up.
Correct.
And this would tell you its speed at any time. I could say, well, what is its speed at 20 seconds? Well, it's 120 feet per second. What is its speed at 1 second? 6 feet per second. So once you come up with the velocity function, now you can tell its velocity at any point in time.
Okay.
Let's try to do 31 because it's a little different.
Got it.
Here we have the area is pi r squared of a circle. And they want to know what the rate of change of the area is with respect to the radius. Well, that means dA dt. Excuse me, that means dA dr. When they ask, oh boy, how did I do that? Okay. dA dr means the rate of change of the area with respect to the radius. You see that? Why that would mean that? And then tell me what dA dr is.
So for area, pi squared, so that would be 9 pi for dA.
Hold on. Just take the first derivative of A. That's what dA dr is. First derivative.
Okay, never mind. 2 pi r.
That's it. Okay, now they want to know what is dA dr when r is 3.
6 pi.
Yep. In other words, I could write this as A prime of r. And now they want to know A prime of 3. 6 pi. The area is changing by 6 pi units. They don't give any units on here. But
no.
In other words, the change of the area is not linear. It's as the radius changes, the rate of change of the area changes. When the radius is 1, the area is only changing by 2 pi. When the radius is 3, it's changing by 6 pi. If the radius were 10, it would be changing by 20 pi.
Okay.
Okay, so all of these problems that look strange, they're all first derivative.
They're all pretty much the same.
Derivative, this is first derivative, this is going to be first derivative. Let's see if we can do 32 real quick. Here we have volume equals 4/3 pi r cubed. That's just the volume of any sphere. And they want to know what the rate of change of the volume is with respect to radius. So what do they want to know? In other words, what does that mean in terms of differentials? Is that dv dx? Is it dv dt? Is it dv dr?
I'd say dv dr.
Yeah, they say so right there. They say, what is the rate of change of the volume with respect to the radius? Well, it's that respect that matters. So it's dv dr. Unfortunately, my pencil stopped working. Let's see if this, maybe I can write with my mouse. No. I got to either plug it in and out again or reboot. Either way, it's going to go past our time. So here's what we're going to do. You're going to calculate dv dr, which would be 4 pi r squared. And then you're going to figure out what dv dr is when r is 2. Well, if dv dr is 4 pi r squared, then when r is 2, you got 16 pi. So the volume is changing by 16 pi per one change in the radius. I guess is the way you would interpret.
Got it.
All right, Taylor, I will let you go. And
okay, thank you.
Talk to you next time.
Sounds good.